In this section, we'll focus on the idea of limits and how we can use them later in the definition of a derivative, for example. So what is a limit? What is this concept? This is the concept of what actually happens to y, or f of x, as x approaches a number from both left and right. So again, we're talking about approaching, so not actually equals to. So here is the notation. A limit as x approaches a of f of x. So this is also sometimes known as two-sided limit, because we can approach the number from either side. Notice how we use this little notation, a with a minus sign on the top. That basically means we're approaching from the left, or you can think of it as the negative side, but it's not always the negative, but it's from the left, or a number that's slightly less than a, or we can approach it from the right, or the number slightly larger than a. So what we need is both of those sides to match. If they match, then the limit exists, and it actually is equal to both the left and the right hand side. If they do not match for any reason, then the limit does not exist by definition. So this is what it looks like. Say if we're approaching the limit from the left, notice we're approaching the whole, so it would be the y value as if there was a y value, because again, we're just getting really close to -1, it looks like. And that's what it looks like. And then from the right, we're approaching the y value of 1. And since the both sides do not match, the limit does not exist. Actually, sorry, 2, not 1. So the limit itself does not exist. Or we can have this situation, the limit as x approaches 0. Now notice we're approaching it from the left, and I'm literally traveling the curve from the left, and notice we're approaching the whole, but that would be the y value of 0 there. And then we're approaching from the right, or the y value of 0 again. So they both match even though there was a whole. Remember, the actual function may not be defined there, but it's almost like an asymptote. We never actually reach that x value, so it would be the same for the y value. It's only what we're approaching. So it would be 0 for x approaching 0. However, at 2, later on, that one does not exist, because from the left, we're approaching, looks like -1 or some negative value, and from the right, we're approaching some positive value. So they both sides do not match, and the limit would not exist. So how we can compute the limit, we can do it in 3 ways, either using a graph if it's provided, or using a table of values. Now, it's very handy to do it with a graphing calculator, or algebraically we can do it for certain functions given certain situations. So let's try a table of values. For example, if you're given an equation, what you can do is put it as if you were to graph it onto y equals 2 on your calculator. Then you may want to adjust your table settings to use a table on your calculator, which is second then window. And what you want to do is make sure that ask is highlighted, because you can input values for x value. So it's on the independent. Leave auto on the y, or the dependent values, because you want them to be calculated. So you want to do that the first time, and usually the setting is saved for later. And then what you can do, this is actually the table that I input on my calculator, and even if some values are there, you can actually start overwriting them. So I would usually go into second and then graph, and then I literally put in, so if the limit as x approaches 1, I put in the values that are slightly smaller than 1. Notice I used 0.9, 0.99, 0.999. And then I used values slightly larger than 1. Now note, your y values would usually be to 3 decimal places. If that's the case, then you may want to put in those values one by one into the equation. That's unfortunately the case with my math lab. Sometimes you have to up to 4 decimal places, but your calculator may not use this. Or you can use, like, for example, here 5.0200, you can try that. Or you can just input 0.9, plug it in for the x, and do them individually. But notice how both at 0.999 and 1.001, so the two smallest values closer to 1, it's actually a value of 5. So both values match, so the actual limit would be 5. Out of curiosity, you can plug in 1 and you'll notice it would be 5 as well. That's because the function is continuous at that value. But again, we don't need to have the actual y value at that point. So again, the answer was 5. And you can do this with other, this is how the table looks like on the homework, for example. And the way I input it is I go back to the table and I overwrite it. So first I go into y equals 2 and put in this function. This is how I inputted it. And then I go back to the table and I put in the first 3 left values, 2.9, 2.99, and 2.999. And then I do it from the right, starting from the furthest right, 3.1, 3.01, and then 3.001. Notice how I have it written. The filled out table looks like this. So first I do it from the left, and then I do it from the right. The reason for that, because right in the middle where they meet, you can see if they match. Now notice here the y values that were steadily growing. Notice you get 12, then 127, then almost 1200. And from the right, it's the same thing, but from the negative. So notice how the positive from the left, it looks like it's approaching positive infinity. And from the right, it's approaching negative infinity. Because both infinities do not match, the limit does not exist. Now you may ask, well, what if they were approaching the same infinity? Well, in that case, depending on the book you use, sometimes if it approaches infinity at all, some books may define that the limit does not exist, because it's usually the limit supposed to be the finite y value that it converges to. But in some books, including this one actually, if both sides go to the same infinity, then the limit would be that infinity. So if both sides were going to positive infinity, then the limit itself would be positive infinity, or vice versa with negative infinity. But since here they do not match, they go to opposite directions, then the limit does not exist. So hopefully that makes sense. Now there is so-called algebraic method we will use in cases there is a hole, for example. We could use a table and a calculator. You could use it every time. But this is maybe a slightly quicker way to do it if you don't want to use calculator, for example. So we need a couple of definitions to be able to do that. First of all, if f of x is continuous, then this is what we'll define in the next section. The limit as x approaches a should actually match the y value at that point. So there's not going to be a hole or some other discontinuity there. And then something else, well, here's how we can use this. Notice how limit as x approaches 1 of 2x plus 1. Now notice 2x plus 1 is a line. Any polynomial, we're going to learn that it's going to be continuous. Then you can simply plug it in as if it was a y value, and you get 3. So if this is continuous, it's very easy. You can just plug it in as if you were plugging in a regular function. Now, all polynomials are continuous functions. The only ones we need to worry about are rational functions, which we'll see. But polynomials are continuous. So we can still do it with a function that has a hole at a point. It's not continuous. So if you plug in x value in the beginning, you'll get 0 over 0, which is also how you know it's a hole. If you'll get a number over 0, and then it's an asymptote, which is a different situation. We'll look at it next time. But we can make it continuous. How we can do that? If you have a limit, notice you can keep the limit, but you can factor the top, cancel the top and the bottom, and what you will get is a polynomial that's left over, or something that's continuous. So where you can plug in the value, which we did, and that's how we get 6. So if you try it with a table on the calculator, you should get the same answer in this case. Notice how we can do it in example 2. Same thing, we'll factor it, get rid of x plus 2 in denominator, and we can plug in -2, and that's how we get the limit. Limits at infinity, it's basically the horizontal asymptotes. It's basically the same exact thing we did earlier in chapter 2. Notice this is a very handy way to look at it. Infinity or negative infinity, the only terms that matter are the leading terms, which is how I wrote it, leading term over the top and the bottom. Notice how x's cancel, so you end up with 3 over 7, and that would be limit of the constant. It's still a constant regardless of what x goes to, because there is no x that is left. Okay. You can do it the same thing here. Notice how we only highlighted 3x squared over 2x squared, so we'll get 3 over 2. And now what happens if denominator is larger? Well, you can still highlight the or rewrite it as a limit with only the leading terms. And now you cancel, you still have x squared left in denominator, in which case, because x squared is in denominator and x is going to infinity, you'll get a very large denominator. But the numerator stays the same, it's a constant. So it's going to go to 0. On the other hand, if x is left in the numerator, like look at number 4, then it's going to go to the same infinity that it's going to. If it's positive infinity, then it's positive, unless you have a negative in front of it. Notice in number 5, it's a similar situation, but you're left with negative 5x over 6. Now, x is going to positive infinity. Imagine very large numbers, but it's times negative 5. So the answer would be negative infinity in that case. And if it was going to negative infinity, then the answer would be positive infinity, and so on. So you can just basically imagine if you have a single negative left, but you have positive numbers, you'll go to a large negative number. And that's it for this section.